invented polymagnetics about 15 years ago because he asked a fundamental question that nobody had ever asked. He wasn't a magnetics guy. He was kind of a deep space communication, electronic communication signal guy. He asked if you could use wave theory and signal processing theory to actually form and shape and design the flux field of the magnet. And everybody goes, of course you can. Except guess what? You can. So he spent about 8 years perfecting the science of polymagnetics. And what you see today is polymagnets. And I'll give you a simple example. These magnets all came from the same vendor, N50, 1-inch magnet, center hole, nothing special. You can get them in any catalog, right? You can see that magnet right there, right? No, sorry, just normal magnet. You're just seeing the screw hole in the center, right? You got a simple 10,000th plate of steel. I'm going to put that on there. You can slide it around because coefficient of friction is very low, but try to lift it off. And you can, right? But it's a good magnet, but I want you to calibrate yourself as to how good it is. Definitely a good magnet, though, right? There's nothing bad about that magnet. It's a good N50 magnet. This is exactly the same magnet from the same vendor, right? Go ahead and take that off.
Oh, wow.
So that magnet is 6 times stronger in attachment than that magnet, and yet it's exactly the same size, same chemistry, same magnet. How's that possible?
Like how you concentrate the flux field? Or?
Exactly, because we know from physics, if we could visualize the flux fields coming out of this magnet, we know 2 things. One, the magnetic forces always concentrate themselves on the edge of the magnet. And if that was a square magnet, they concentrate in the corners of the magnet, right? We know that, right? Because you can go to any of these characterization companies here, run a scan across that, and you'll see it blip up at the corner, come down, and then blip up at the edge and come down again, right? So if I have high concentration of flux on the edge of this, what's the fastest path for me to go from north to south? It's right around the edge here. So I have all of these little edge effects, right? All these flux fields going around the edge of the magnet. When you use a magnet in design, you almost never have your plane of work on the side of a magnet. It's out here. Because the majority of flux field is out here, right? That's where we're focusing it. So all these little edge effects that go around the outside are really completely wasted in our design. Now the other problem is long field. You can see that the field goes right through that 10,000 steel. In fact, you can see the field way out here. See it?
Mm-hmm. Yeah.
So these long fields that go through the steel, those also aren't doing us any good, right? Because they're on the other side of the steel. So unless I'm attaching this to like a tank or an anvil or something really thick, right? I have a problem. But in today's design world, what do we want? Light, thin, cheaper. Right? We're going the exact opposite direction. So we need to think differently about magnets because otherwise we're going to lose most of the potential energy. So all we've done is I think of this as having a certain amount of potential energy. The question is how much of that energy goes into the function that I'm looking to achieve. By creating polymagnet, we've been able to now create multiple poles on this magnet. So now the fastest path from north to south is actually across the face of the magnet. And because of that, more of the energy is being used in my target application, which is a plate of steel right on the other side of this. So we can increase a magnet like this anywhere from 6 to 10 times attaching to a thin piece of metal. So that allows you, if you think about it, 6 to 10 times, I can go from an N50 to an N30. I could go from an N50 to recycled material. I could go from an N50 to a ferrite 5.8. So I could any magnetic material. So that's just showing you attachment. But then you go to another example. This is about EMI and medical safety. So in this case, you can see again, this blows straight through the steel.
Yeah.
So I can't put this anywhere near a pacemaker. Right? That's why you always say pacemakers say, don't blah blah blah. I can't put this anywhere near a computer or a screen or any kind of circuit board because you can see the field will start to interfere from an EMI perspective. I move over here, nothing. 100% of that field is captured
through the steel, right? Yeah.
10,000th of an inch. 100% of that is captured. So I can put that on right on the case of a pacemaker, and it won't go through the pacemaker. I can put this now on the back of a monitor. I can put it on a PCB board. I can put it in a camera. I can put it in a credit card reader. So the ability to use magnets around electronically sensitive areas and medical devices, right, is also enhanced. So increasing forces, getting more use out of potential energy, safety medically, and also EMI safety. But then another opportunity is to combine forces. Or I should say combined functions, have more than one function in a single magnet. So a simple application of this is always this, I always love this one. This magnet attracts, and then it stops. And now it's a spring. So it attracts here, and then it stops. So it's two different functions in one magnet. So it becomes a hovering spring. But the attract function keeps it together. So the assembly is held together with a long force, but the short fields prevent it from ever touching each other.
How does it behave, let's say, if I heat it up? Does the field lines stay together like the way you magnetize? Let's say if you heat it up or cool it down.
So it's the same properties of whatever the magnet is. So if you have a standard neodymium, it behaves like that. If you add H or S, heavy rare earths to it, it acts exactly like that. We don't change the chemistry, we don't change the structure. So the base magnet that you buy, those are the qualities of the material that you are going to get once you magnetize it.
Polymagnet chemical composition is rare earth?
Could be anything, sure, anything.
It's the same,
Samarian
same
cobalt,
magnet.
Samarian cobalt, allantoe, ferrite, bonded, anisometric, isometric. It doesn't matter. If it's permanent magnetic material, we can magnetize it. But you deal with all the characteristics of the material that you use. So if you're using bonded, isometric material, you're going to get the behavior of isometric bonded material. So this is one
you
of
guys can design the field lines.
So we have software that helps you design all these crazy patterns so that you can very quickly come up with a design. And then we have prototyping equipment that allows you in minutes to make the magnet. And then of course we have production equipment if you want to make millions of magnets.
Yeah, we have an engineer over there doing design right now. He can do a design on the fly, and we can make them immediately.
Yeah, we'll
Right
show you in
here.
a minute. Well, but here's another one. This is rotational. So this magnet is a spring, but if I rotate it, it's a latch. If I rotate it again, it's a spring. So there's just a million interesting combinations here. I think you've seen this as a shear, right? So in this case, magnets aren't good in torsion and they're not good in shear, right? That's how you get magnets apart. So that means you can't use them for magnetic couplings or transmissions or shear pins or anything like that, right? Well, all you have to do is design the magnetic circuit so that it does that. So in this case, we've designed these. Obviously, they're going to be hard to pull apart, but you should be able to rotate them or slide them, right? They're magnets, but you can't move them at all.
Yeah, we're used to being able to slide.
So you could use this for a magnetic transmission. Go ahead. You could use it as a magnetic coupler. You could use that as a gear. You could have a gear ratio where you could have a different set of poles on one side than the other, and you can have a gear reduction contactless with an air gap in the center with absolutely no frictional surface transmitting force between two motions. And all of that is accomplished by changing the magnetic pattern on an individual magnet. These are simple. They started as very simple.
Regular standard magnet.
Standard magnets.
We just put them in the machine, and in a matter of seconds, they're a polymagnet.
But you can see
With
the delicate
thousands
patterns
of
that you
magnets
have.
now.
And there's a million other things that you can do. Like this one,
It's like a curved magnet.
you can do curves. So there's multiple ways to do a curve. If it's slightly curved, you can just do it in a planar magnetization. If it's highly curved or a cylinder, then you have to change on our equipment the material handling so that you're rotating the piece as you magnetize
Axially,
it.
right.
That doesn't come on the standard piece of equipment. That's kind of a customization that you have to have. I think I showed you this, which is the multiple functions, which is concentric alignment, high shear, and 15-degree rotation.
Oh, I
right? So you get all of that in one magnet.
But have you used this technology like in automotive or some?
Yeah, Tesla used it in their original, what was not the Roadster, but the first big production car that they had that came out. I remember what the Model S.
Model S.
Model
That was
S.
What was the
good.
It was an internal for their entire center console to actually kind of activate it and lock it into different positions. They use Polymagnet.
Have you used this in a motor?
We have not, but we've had two motor companies approach us with problems that they had.
They
We're
seem-
not motor designers. We're not product
They seem
designers,
excited
right?
about it.
And the two basic motor problems that the different companies have come with, one was an aviation motor company, so it was very high power. And there, those edge effects that I talked about, they cause all kinds of heat problems because you have all this power, right?
But you gotta get
I
that
mean, the
stuff.
magnets get demagnetized. Or the demagnetization happens.
Yeah.
Yeah, we're not motor designers, right? So so they came to us to say, how could we design our magnets to get rid of edge
With a better
effects,
curve.
right? And then we had another company come that looked like they were dealing with very small axial flux motors. Looked like for robotic type applications, right? And there they were trying to deal with very lightweight, very thin stators, even all the way down to PCB board type axial flux motors. And the problem is they can't generate enough torque. And the reason they can't generate the torque is because the reactive surface is so thin. But let me demonstrate how we deal with thin reactive surfaces. This is actually just paint. The only thing in here are teeny iron filings. So this is a normal neodymium magnet. And you can see there's very, you can feel there's some attractiveness, but man, there is not very much adhesion. That's a polymagnet. So if you can have that kind of attractiveness, right, on a few iron filings, then the ability to create torque in a PCB kind of based axial flux motor, right? What does it require? It requires an optimization of your flux field to be extremely thin and tight. You don't want long field. I mean, long field there could be 2 millimeters, 1 millimeter. That's a long field because because it's so thin, right? So you want it to be very thin and you want no edge effect. So
you have design services. You can do the
yeah. So we will either do everything for you, or we will give you everything to do yourself.
Yeah.
Or we'll do technology transfer over time. We'll start by helping you, and then over time you learn, and then we'll sell you the software and you can do it yourself, and we'll sell you prototype machines and you can do it yourself, and eventually you can do everything yourself.
Is there like some patent on it?
Yeah, there's 180 patents.
Okay, so then if you want to use your technology,
It's
Yeah,
licensed.
give the license.
yeah. You buy the equipment, you get it.
So I wasn't sure, like, do you supply equipment?
Yes, we do. We do. The software and equipment. Or
Oh, is it your own proprietary software?
yeah, the designs this kind of
Is it
stuff.
2D software?
Yeah, you'll see it. I mean, it creates a 3D object.
It's a CAD software.
You import any kind of CAD model, right? Or standard magnets, which are 3D objects. We use SolidWorks, but you don't have to. And then this helps you actually manipulate all the patterns really quickly. And then it produces two files. It produces a tray, so that goes in the machine because your magnet may be
Different shape.
an odd shape, so it makes a tray for it. And then it also produces a production file that will literally go through and magnetize. And that's up goes to the machine, put the magnet in, and you magnetize it.
You get instant magnets.
So it allows you to
Make it into
So let's say I want to do analysis, right?
So it exports a step function to ANSYS, and we use ANSYS, but you don't have to use ANSYS. You can use any magnetic, whatever you happen to use. But we export a step file. We don't natively integrate because that would be a lot of work to natively integrate to every single,
every change. Yeah.
every change and every model. But the step files are fine. So that's what we do. We export it.
I mean, I think